So let's move down to the second part of the morning, plate tectonics and orogenic cycle. So we move from continental drift now to plate tectonics. And plate tectonics was really put together in the 60s of the last century and was built up from geophysical data on oceans, exactly the opposite as continental drift, which was built on geological data on continents. And it stipulated the lithosphere crust plus lithospheric mantle, so the upper part of the upper mantle, is subdivided into a dozen plates that are moving relative to the asthenosphere. In some places, plates are diverging, and this corresponds to mid-oceanic ridges, and it's causing thinning, extension. We see, I'm going to use that word, but I think it's very confusing, and I need to define exactly what I mean by that, and sometimes in the literature you'll find it's used in different ways. Plates in other places converge relative to each other, and that is accommodated by subduction. Subduction being the motion of a plate beneath another. But really, plate tectonics started a bit before that. The 60s have been highlighted as a historical moment where geophysics and geology came together. But there was a brilliant guy, Holmes, that set up all the evidence before the 60s. And first he realized, okay, if we rely on Earth rotation as the main driving force for continental drift, then the dominant force available tends to set up a westerly drift due to tidal action and a drift from the poles towards the equator due to departure of a polar section through the Earth from a circle. So basically he said, okay, when we look at the present day mountain belts, they're not consistent with that. So we need another force. And this other force, radioactivity, has just been discovered a few years before, and the radioactive content of rocks was also identified at the time. So he sort of evaluated the thickness of the mantle, its content in radioactive elements, basically uranium, thorium, potassium, and he calculated the viscosity or the temperature of these rocks and then their viscosity as a function of the radiogenic content. And he says, well, that's consistent with this mantle to be gravitationally unstable and to be activated by convective motion, convection. Convection currents may be set in the lower layer as a result of differential heating by radioactivity. And this is his representation of upwelling, downwelling, and represents Gondwaland, Tethys, Laurasia, North Pacific, South Pacific. Everything is set here for the large-scale picture. And at the same time, he applied that to use the knowledge of lithosphere. And you see here a continental block on top or laterally connected to an old ocean on top of something that looks like a lithosphere, the mantle lithosphere. So he identified the lithospheric plate. And he says the effect of compression on gabbro would be to transform the material into eclogite. Eclogite, for the bachelor students, is a rock with garnet and pyroxene, which is quite heavy, quite dense. Such a change of density and the simultaneous action of isostasy would lead to the formation of oceanic deeps, trenches. So I identified, so these crosses are eclogites. These are the places where the lithosphere goes down because of its weight. Remarkable. And he also put mountain system in there as places where the downwelling occurs. So that's, I think, the first steps for plate tectonics and mountain building, orogenic cycle. So nowadays, plate tectonics or lithospheric plates are identified thanks to localized volcanic activity around the Pacific, but also along the Alpine belt, so it's not as well organized, and also along rifts, such as here the East African rift. There are other places where there is volcanism, which is not really mentioned here. It's all along these ridges, there are lots of magmatic activity. And some hotspots, Iceland, Hawaii, places where there is localized magmatic activity, volcanoes that are not completely linked to plate tectonics, such as Hawaii. Iceland is on the ridge. There's also localization of earthquakes, earthquakes with different depth of their hypocenters. Depth that is here indicated by colors. Red is the surface. Well, let's just think that might be also an exam question. Describe the distribution of earthquakes, integrating also the color scheme for depth of the hypocenters, and identify the different type of plate boundaries. So I'll let you think about that just 1 minute. Look at the colors, how are they distributed? How are these mid-oceanic ridges in the Atlantic, Indian Ocean, Pacific? How are they distributed? Shallow or deep earthquakes? Shallow. Shallow, so diverging plate boundaries are characterized by shallow earthquakes, less than 30 kilometers. And then if you go along the Pacific, what do you identify? Colors are changing. Red, orange, yellow, green. What does this mean? Subduction. Subduction, and you can identify the polarity. And there's the polarity, it's deeper towards the west here, so the plate is plunging towards the west. So we see that along the Pacific, West Pacific, East Pacific, same thing. So if you have an oceanic plate converging towards a continental plate, same thing happens. So there is subduction there too. But here, the polarity is towards the east. What about the Alpine Himalayan belt? Alpine Himalayan belt. What happens here? Type of earthquakes. Mostly shallow, but there are lots of shallow earthquakes that are distributed. It's not as restrained in space as along oceanic plate boundaries. So it's distributed in space, but there are some deep earthquakes there that are also kind of hidden below the red ones. So what does this mean? How would you call that type of belt? Just spontaneously. Alpine Himalayan belt. Continental collision. That's, I think, the most common way to describe this. What are these deep earthquakes telling us? More than 100 kilometers. Might be colossal, but we'll see that from geophysics, we do not find evidence for having crust as thick as 100 kilometers.
It's not as thick, it's just like yellow. Right?
Yeah, 150, it's 150, but it's difficult to read from where you are. So we have here earthquakes that go down to 150 kilometers, and especially here, here also, here. Here it's not identified, but it's also the case. What does it tell us? Suture zones, and how is plate convergence accommodated in these places? If there are earthquakes as deep as 150 kilometers. Subduction. So it's a subduction collision belt. We start to have a problem here of terminology and concepts. But we'll clarify that right away. So these were used, these geological evidences were used to define the first lithospheric plates in the 60s. And that leads to the scheme that is here reproduced from a figure from the Geological Survey of the States and of America. That's an interesting one. Look at the Eurasian plate, North American plate boundary. Well, see that Kamchatka and part of Siberia is North America. Huh? If you thought that you were doing neutral science, this is highly political. Where do you see the evidence for a plate boundary? In terms of seismic? In terms of volcanics? If I had to make a choice, probably we'll put it here. No? Very politic. Nobody cared about this place of the world, 20 years ago. But now it's a very touchy place because thanks to climate change, the ice is melting, right? So all these new continents shelves are going to be exposed, and there are lots of resources. It's a place where you can also travel, from one place to the other, of the earth to the other. So they are very, very important. So I think we're going to play an important role just at delimiting plate tectonics, and we're going to be asked soon. Okay, does this place belong to Russia, China, or North America, or You'll see.
So, in the earlier slides, if the subduction is occurring, then shouldn't the yellow points be in a greater number and in a linear fashion along the plates? There were just
start again.
You told that the yellow points,
yes,
they were due to subduction, right?
Yes.
But there are a greater number of red dots along the area.
I know.
If subduction is occurring, shouldn't there be more number of yellow points in a more linear arrangement?
Yes, you're right. So this is a what you're saying is that there is not an alignment of these yellow points all along the belt. Huh? This is correct. Huh? But that's I think it's 5 years of record. So they are not as the recurrence is not as great as in the ocean continent subduction, but they are there. How continuous? That's also a question, and we'll see that in the next few slides. But it's a good question, I think.
So my question is somewhat contradicting to this. So what I ask is that even if there is subduction, so how are there so many earthquakes possible below the thermal LLE?
Next slide. We'll see that. No, but I think I put some kind of seed in your mind, and it's growing. It's good. But that will come at the end of the presentation. First, we start with the basics of plate tectonics, and you asked me for that. Huh? And well, it started with the middle of the oceans, birth of the ocean at mid-oceanic ridges. I started with I didn't put the slide, but with the topography of the ocean was reconstructed first with a cable that served for telegraph. So that was taken from Europe, London, and Great Britain to New York. And they went with a ship and left the cable going down to the ocean floor, and then all of a sudden, in the middle of the Atlantic, they realized that they didn't have to go for 4,000 meters, but only 1,000 meters. Oh, there's a ridge there. So that was the first image of the mid-Atlantic ridge, was because of the cable for telegraph. But then it was improved a lot, thanks to the Second World War, right? Because many ships were there trying to find submarines, so they measured bathymetry, and they measured magnetics, identified the metals. Lots of knowledge, unfortunately, comes from war and armaments. Huh? We know that. And most of our scientific knowledge comes from that. That's a pity, I mean, from my point of view, but that's the way it is. It's a luck that some people from these, especially here the American Marines, they thought, okay, now the war is gone, is finished. What can we do with this data? So they managed to use this data to build the bathymetry and the magnetic anomalies of the oceans. Here it's a seismic wave velocity image, so it's difficult to read, but you see here that there is a less rapid material beneath the mid-Atlantic ridge, and that was discovered by Ewing in the late 50s. Here the magnetic anomalies. So at first, the record is not as, that's the original image from Vine 68. All these now with the internet is easy to find. So if you take just a reference and you put the correct words like magnetic anomalies, you find this. So this is how they look. Here that's close to Iceland along the mid-oceanic ridge of Atlantic Ocean. So from that repetition, he had black, white, black, white, black, white, centered on the Atlantic Ocean. They reproduced, with that's the average magnetic field, and so I took that from a sort of general textbook, and you had some places where it was above, below, above the average magnetic field, and that was interpreted as being related to trapping of the magnetic anomaly, magnetic orientation at the time of crystallization of the basalt that forms the ocean floor. So you see this black vector going up or down in the red and white stripes. And this is really magnetite minerals that are in the basalts and are oriented at the time of cooling of the basaltic magma, in the orientation of the magnetic field. And what they identified was either pointing towards up or down, but with the same direction. And that's up, down, up, down, up, down. So the idea was that in between the emplacement of that basalt in white and which is now here in the next step, and this red basalt, there was an inversion of the magnetic field. And by this way, we can reconstruct, by dating all the inversions, we can reconstruct the expansion of the ocean from the mid-oceanic ridge. Divergence, thinning will lead to, so I'll do a shortcut here, will lead to decompression of the mantle underneath, and decompression leads to partial melting, generate a basalt that is placed at the surface to form the new crust. And then divergence again. This new crust is separated in two. These two stripes that formed only one here are there. And then another event of magma extraction occurs, but in between there has been a switch or reversal of the magnetic field, Earth magnetic field, and so on. So this was for birth of the oceanic lithosphere and crust, actually, but we'll see how the lithosphere behaves. And then what happens to it? Well, it's being recycled along convergent plate boundaries marked by trenches, such as here the Mariana Trench in the Western Pacific. And the process here is one plate goes beneath the other, and it's identified, illustrated by the depth of hypocenters. So that this is the Mariana Trench here. And you see its shape, that's a map view. And we're now going to see cross-section views that are here. So here you have the distribution of the hypocenters of the earthquakes at depth, which are called the Wadati-Benioff plane, because there are two persons that developed that, made that observation. Wadati, who's a guy from Japan, no surprise, was very concerned by earthquakes. Benioff is German. These guys are not much concerned by subduction, but in Germany, there is a history of technological development. So it also explains why they made that type of discoveries. That was part of your question, the distribution of earthquakes. So you see here there's a diffuse zone of earthquakes on both sides of the plate boundary, and there's a localized zone of earthquakes which delimits the plate that is going down. So it's both. You have long convergent plates, you have diffuse zones of earthquakes and deformation at the surface, but also localized at depth, with some holes in there. So there are some things that are happening. That's not a continuous process. And we'll not see it, but it's probably related to metamorphic reactions, water release, and the behavior, who was asking brittle ductile behavior of plates as they transform into minerals related to metamorphic reactions. So we have seen birth at mid-oceanic ridges of oceanic crust and lithosphere, recycling along subduction zones. Now plate tectonics needed a mathematical model that came from Euler. Euler is a German mathematician who studied all sorts of problems, not particularly geology, but he proposed that, he elaborated that plate motions on top of a sphere are defined as rotations with an axis that goes through the center of the sphere. And this has been applied then to plate tectonics. In this case, the motion of one plate can be defined as one single angular velocity vector. So that's the beauty of plate tectonics. It's very simple. But it requires also that plates move like this, opens. So it opens like a scissor with a maximum opening along the equator of relative to the axis of rotation and 0 at the axis of rotation. And this doesn't take into account the recycling along subduction zones, only opening. So what happens here? Does this really account for the features we see along tectonic plates today? Not really, not exactly. We see this scissor-like opening, but we don't see a continuous zone, a boundary like this. What we see in the Middle Atlantic, for example, are transverse faults that are cutting across the mid-oceanic ridge. And these transform faults are transfer zones. Here's the San Andreas one that is going here from the mid-Pacific beneath or intersecting with North America. That's San Andreas. San Andreas is here, San Andreas fault. And you see that there are mid-oceanic ridges are represented like this, and transfer faults are like that, perpendicular to the ridge. That's the one in between the Arabian Peninsula and Africa, with same ridges, transfer faults. So that's a schematic representation by Isaacs, 1968. So all happened in 1 year. All these were put together in 1 year. The subduction, opening of the Mid-Atlantic ridge, and so on. So if you see a ridge like this, another ridge like that, and a fault in between, what kind of earthquakes do you expect here, and what kind of motion do you expect in between these two segments? So we're going to vote. Think about it. Is the top part moving towards the left or moving towards the right? Be careful, there's a trick. I'm not going to make you vote because I don't want to make you feel uncomfortable. But first, the logic was, okay, this has been moving towards the left, it's been offset towards the left. But the earthquakes that were identified along this zone were all indicating the opposite. And that's why it's called transform zones. Because really what it does, it accommodates differential opening along different segments of the mid-oceanic ridges. So here it's opening like that. Here it's opening the other way around. So in between, the motion is like that. But it took them a while, you know. At first they were thinking, oh, that's strange, you know, maybe we made a mistake in our interpretation of the earthquakes. So it took them a while and then they understood it. The question now, I think, which is still unresolved, is why these transform zones, well, let's put it another way. That means that this ridge was never in continuity with this one. Why isn't this the case? In this scheme, there's one ridge. And we understand that differential opening might be accommodated by these transfer zones. But why is the ridge offset? That's a question for you guys in the next, for the next PhDs. I'll put you some ideas to work on. Probably has to do with the distribution of cratons, hard spots. Where the weak spots are, where the hard spots are, is going to control where the geometry of opening. You know, we're not opening an homogeneous Earth. It's opening with lots of heterogeneities that are going to control the place where the offsets are going to be localized. That's another question here. This is nicely drawn. It's taken from a picture which represents mid-Atlantic, the Atlantic, North and South America, Eurasia and Gondwana, or Africa. And here you see that the axis of rotation is not totally random. Can you see something? Malika? It's almost coincident with the Earth rotation. Huh? And it's been killed in the egg. Wegener proposed that Earth rotation was a force controlling plate or continental drift. But the geophysicists said, oh, that's too small. As a geologist, I think there is something there. You know? We'll come back to that later on. So these transform zones are necessary to accommodate differential opening of oceans and also differential subduction related to the fact that motions of plates on top of the sphere are rotations. And the shape of these transfer zones, they are slightly accurate and corresponds to big circles in the stereographic projection, big circles. So the curvature was used to identify the pole of rotation. So what these guys do, Isaacs and colleagues, in the 60s, they identify all the transfer zones, drew lines perpendicular to it, and saw where they would connect and identify the poles. That's how the first poles were identified, poles of rotation. And then they measured displacement relative to the ridge and identified that displacement was symmetrically decreasing from the, not from the ridge, from the pole of rotation, was the motion was symmetrically increasing relative to the pole of rotation. So our first pole. Second way to identify the poles is to use the poles recorded in rocks on the continents that show an apparent polar wonder. For example, if we measure a pole trapped in Eurasia, in green here, in rocks that are 500 million years, the pole was here. If you measure the same pole 500 million years ago in rocks from North America, it's here. So it shows an offset. At the time where there are two poles, two magnetic poles, So that's the magnetic pole, not the rotation pole. Huh? I changed topic here. Today, if we measure the pole, it's the same place for both North America and Eurasia. 100 million years ago they started to be offset, more offset 200 million years ago, and even more as time proceeds. So either the pole was wandering and was not the same for North America or Eurasia, or another way to explain it is to move the continents and make the pole match and the continent move. Instead of having the poles moving, make the continents moving and match the poles. And that leads to that reconstruction 500 million years ago and opening of the Atlantic in several steps. So we now have all the tools to reconstruct plate tectonics. We can identify with the transform folds the poles. We can then have a model of plate motion with the transform folds with the axis of rotation. We come back to that. No. We can also measure the displacement along mid-oceanic ridges by dating the rocks on each side of the mid-oceanic ridge. And this was done since the years. It was done throughout the years. And this map, it really reflects, you can see all the different rectangles. Each rectangle corresponds to a magnetic anomaly, black or white, black or white. So these are only binary maps, black, white, and the colors have been put by ages. And if you look at how many ages we rely on, it's not that much. There is one section here, maybe one here, and there are also one or two sections in the Pacific where the deep drilling has allowed to date rocks. So this is really a conceptual model that relies on a few data. And it's really binary. And with binary reasoning, if one step is wrong, boom, everything falls down. Huh? So I think that reflects, it's very simple, it's very nice, but it reflects the lack of data as well. Nevertheless, we have a map of age going from red, 0 to 200 million years in blue, and you see the symmetric distribution of colors, ages relative to the mid-oceanic ridges. And for the Atlantic, it's very nice. It's very nice, symmetric. The oldest are on the margins, the North America and Africa margins. And we can reconstruct the opening of the Atlantic, first here in the central part, and then move towards the northern and southern parts, and then finished with the northern part. This continued that was like this, and then like this. Very symmetric. And there's no subduction on the margins here. So that's why the symmetry is well preserved. In the Pacific, the symmetry, let's take we'll finish with the Indian Ocean. The Pacific, we see that symmetry here, fairly well preserved, but starts to be unbalanced here with an very old lithosphere along the Marianas. That's where it's very deep, steeply plunging. Whereas here, the ridge is going into subduction. That's a strange, peculiar feature. That's not explained by plate tectonics, by basic plate tectonics. So we come back to that. So there's strong asymmetry here. There's a strong west-east asymmetry. So the Atlantic opening is consistent with an axis of rotation, almost coincident with the Earth rotation axis. And the Pacific, for this part, is also well organized relative to a north-south axis of rotation with a strong west-east asymmetry. So there is kind of a west drift, something that goes with west-east asymmetry. So in order to to reconstruct plate tectonics, we need a reference frame. And that's something tricky. What is fixed? Everything is moving. So how do we measure? We measure relative displacement across plate boundaries. But can we measure absolute motion? Very difficult. So at some point, they thought maybe the hotspots, the volcanoes that are not related to plate boundaries might be fixed, and these strands might record the motion of the plate relative to a fixed point. And these are the hotspots represented in that figure. But by doing that, it works, somehow it works at first order, but then we see that also the spots are moving relative to each other. So it's not that fixed. Finding a fixed reference frame is not something easy. So the principle here is that if we look at Hawaii, the active volcano is here, and as you go along this strand, these are old volcanoes, and the oldest is subducting here. So you go younger, younger, younger. Here there was a kink in plate motion, sometime during the Eocene, close to 60 million years, and then a regular trend. So the idea is that the hotspot is related to melting of the mantle, but at depth, very, very deep, not as in oceanic ridges where the melting is close to the surface. This magma is punching across the plate, making a volcano, and as the plate moves, the hotspot remains in the same spot, and the volcano moves out of the place of magmatism, and the old volcano might be eroded and then fade into the deep ocean. So with all this data, there were two guys that put together the same kinematic frame, an American, Morgan, and a French, Le Pichon. Le Pichon started his PhD thesis with the idea of demonstrating that plate tectonics didn't work. So that's another lesson. You know, when you start your PhD with an idea, you might change on the way. You know? So that explains why he was 6 months late compared to Morgan. These guys were in competition, you know, and they wanted to publish as fast as possible their model, which is really a kinematic model that relies on identifying the plate boundaries, the motion, relative motion across plate boundaries, so divergence, convergence. And then when you have measured the motion of A relative to B and the motion of B relative to C, you can compute by vector addition the motion of C relative to A. That is what plate tectonics is. It's a kinematic model. And it's roughly the same. So the main hypothesis is that lithospheric plates are rigid. So if the plate is moving, I shouldn't do that. If you have the motion of one point, you have the motion of the full plate. That's very elegant mathematically. Plate motions are rotation about axis passing through the center of the Earth. So the plate motion is defined as a single vector of angular velocity. And relative motions are calculated by vector addition. So that worked fairly well. I made an exercise when I started to teach tens of years ago. I took the paper of Le Pichon and I tried to reconstruct plate motion with addition of vectors using his numbers. When you use his numbers, the Atlantic is closing. He made sign errors. And it tells you how fast these things were tried to be published and how bad the reviewers did their job. I was surprised. You know, it took me 3 years. You know, I did the first year. I said to the students, "Okay, used all nil, bad grades." Second year, the same results. Because I didn't do the exercise actually myself. I just gave it to the students. I thought they would give the right answer. 3 years after 3 years of having the Atlantic closing, I said, "Okay, I should do the exercise myself." I realized there was an error of signs. Even in papers that are foundations, you should be careful. You should be always cautious about what you read. I'm not saying that these guys were not honest. It's not a problem. They were too fast. And so that's a lesson also, I think. not everything that is said in the book is right. So you should do your homework carefully, robustly, rigorously. Driving forces, so I'm not going to spend too much time on that. People have thought about convection, mantle convection at different scales, only for the full mantle, with different convection cells in the upper mantle, lower mantle, some kind of mixture of the two. Basically, mantle convection might be a driving force for plate tectonics. Slab pull and slab push. We've seen in Holmes the idea that the density of the plate might also play a role by pulling, that slab pull. Ridge push, I think the term is not very good. The idea was that at first the magma could push the plate, but the magma pressure is not big enough, now we think, or we can calculate, to push a plate. So it's mostly, we'll see that in the next hour, it's mostly an uplift of the plate where it's thinned, and then glide by isostasy. But the ridge push term has remained in the literature. And then you have active rifting versus active rifting. Have you seen the nuance between the two? It's very different, except that everybody's active. So active rifting for people looking at global scale, that means mantle and lithosphere, is this type of rifting. That means that here there's an upwelling from the deep mantle that causes uplift of the surface and then gravity glide of the topography. And it's active in terms of where the asthenospheric mantle is the main driving force. So the guys, mostly geophysics, talk about active rifting in that case. In this case, it's plate tectonics that drives divergence, thinning of the mantle, of the lithospheric mantle, upwelling of the asthenosphere that then feeds the process, and that's active rifting for these guys, looking at lithospheric plates. And for these guys, passive rifting is this. For the guys here, passive rifting is this. You'll find that in textbooks, be careful. Would you prefer to see yourself as active or passive? Well, it's the same for geophysics and geologists. No? Geophysicists think that this is active. Geologists, tectonics, think that this is active. Matter of terminology. Terminology. If you use the same words to say, let's say, if we use different words to say the same thing, it might be confusing, but we might understand each other. If you use the same words to say different things, then it's getting very complicated to communicate. So the driving force for plate tectonics. So Earth, driving force, sorry. Yeah, the last one, so I came a bit onto it, is Earth rotation. And this, I think the fact that the Atlantic is really consistent with an axis of rotation, consistent with the axis of rotation of the Earth, is compelling. And this was killed in the egg in the 60s, and even before, people thought that this was not enough. And one or two teams that worked on that, Dolioni, from the 90s, worked really hard on that, and he really became paranoid because the full community was against him. Okay, you have strange ideas, And he said, okay, but there are asymmetries along plate convergence. There are plates where you have opening of back arc basins, and plates where you have no back arc basins, and you have mostly thickening of the crust. So I propose that there is an effect of relative motion between the lithosphere and the asthenosphere, or the deep mantle, that connects to that explains this asymmetry. So I will not go too much deeper into that, but I think there are many evidences that Earth rotation should be taken into account. And if you look at these type of projections rather than the ones that I showed you before, looking at this, of course, there is a huge biased because we represent a small surface as a very big surface, and there's big distortion. Here the distortion is much less important, and you see the Atlantic Ocean and the mid-oceanic ridge is almost coincident with the pole. Here the situation might be more complex, the South Pole, because the South Pole there is a strong continent here. So again, it's fairly symmetric here in the Indian Ocean, in the Pacific as well, it shows here, but then it tries to go around this strong nucleus, and that might cause some kind of discrepancy relative to the Earth rotation axis. So plate tectonics is really driven by dissipation of internal heat, which leads to gravitational instabilities, convection, gravity slide from the ridges, slab pull as the plates get denser along plate convergent plate boundaries, and Earth rotation. Okay, so that's plate tectonics. I see you taking notes. That's the history of plate tectonics. So now we're going to put orogenic cycle into that frame. I think you have all these slides, but it's good to take notes. I agree with you. You should take notes, and I also advise you to draw things. I made my little inquiry as a teacher, and also think about pedagogy. I see, it's not the case here, but my students in France, they now all have their cell phones taking pictures all the time of me and the screen. I say, are you sure you remember things? Oh, yeah. And then I see the exams. Okay, I agree. Maybe I'm not a good teacher. You know, I take my part of responsibility, but I think it's very important to take notes. And I looked at the work of people doing how do you call that? How the brain works, and it looks like things are going from the hand to the brain. So it's important to draw things. I know myself, the first time I draw a tectonic scenario, it's difficult. It's not coming easy. And after I do it several times, then it starts to make sense, and starts to be more fluent. I'm sure if you do that, you'll feel the same way. So I think it's important to draw things, to take notes, and even though you have the material, so it makes you feel more comfortable to say, okay, I've got time, but things that are important, take notes now. Neuroscience. Yeah, neuroscience that tells us that it's important to take notes. If you type on the keyboard, it works, but less than when you draw by yourself. So orogeny, how was it incorporated in the frame of plate tectonics? Well, at first it was subduction was followed by collision. When two continents would come into contact, that is called collision, and that's the end of subduction. That's what these guys, geophysicists, thought. And the rationale being that the continental crust is too light to subduct. So it resists subduction and it will stop subduction. And at the time, so I put that map again. Look at here, so I have to make a bit of zoom. Complex series of arc-like zones. What does that correspond to? That's the Alpine Himalayan belt. And the geophysicists, how do they describe it? Complex series of arc-like zone. Complex, well, that means that's difficult to understand. Arc-like, you're not really sure about what you're talking about. What it really tells us is that Mackenzie or his Isaacs and these guys, well, they couldn't make something out of the mountain belts. They couldn't make sense of it in the frame of plate tectonics. So it required the input of geologists. Dewey and Bird put the first compelling integration of orogenic belts in the frame of plate tectonics and defined two different types of orogenic belts, collision type belts, which qualifies for the Alps Himalayas, that are characterized by a period of oceanic subduction, with here some deformation of sediments, with sedimentation in a marine environment, and then at some point the collision occurs, and the contact between the two continents would be marked by a suture zone, an ophiolite, which is here. But it's also characterized by these blue nappes, high pressure, blue schist eclogites, high pressure, low temperature nappes, which means burial and exhumation. We'll come back to that later. And that's also marked by, at the surface, a transition between the flysch, which is now called turbidites, so deep marine sedimentation, to molasse, which is now called conglomerate, coarse-grained detrital sediments, continental sediments. So that means that there was an uplift of the surface from below sea level to above sea level, and that corresponds to the formation of the mountains. So this is all recorded in metamorphic, in geology, in sedimentary rocks by deformation and by metamorphism. And then they distinguish that from the Cordilleran type belts, the peri-Pacific, where you can see also high pressure rocks, here in purple. But also there is a belt in more internal position of high temperature rocks. So high pressure and high temperature rocks, which in their model, they relate to here the emplacement of magma. So implicitly, they propose that this high temperature is related to contact metamorphism. We talked about that, I think, with one of you guys. Say, okay, what is the input of granite, magmatism? So here they said, okay, that's probably what causes the high temperature, the rise of isotherms in this area compared to this area. But they also here invoke, without much describing it in the text, normal faults that are related to coastal extension. And you see these arrows. And that reminds a bit of the model of Scrope, you remember? With the magma going into the internal zone and the sediments gliding towards the external zones. I'm not sure these guys realize that, but they probably had that in mind. You know, everybody has some history, so you need to understand your history and where you come from, what is your background, and how it influences your ideas. Because this is not described in the text; it's represented in the picture, not described in the text. So at the time, there was also this idea developed for the Himalayas of indentation, rigid indenter, meaning that India was strong relative to Eurasia. I'm not sure if there's something politic behind that, you know, but so you think about the strong India punching into Eurasia, and the consequence of that would be extrusion of blocks, Indonesia, China, South China, towards the east, localized along shear zones, continental scale shear zones. But what these guys first showed, and we come back to the indentation model afterwards, it showed that collision didn't stop convergence. Because this suture here can be dated. And it's dated at about 50 million years ago at least. So it means that collision between the Indian and Eurasian continent occurred 50 million years ago. And since then, India is still moving. Collision doesn't stop subduction. If we come back to that schematic representation, collision doesn't stop convergence. So I also here mentioned something important. You don't want to confuse plate kinematics, motion of rigid plates, that are measured far from deformation zones, with deformation, orogenic, tectonic zones. There you measure deformation, shortening, lengthening, and we come back to that tomorrow morning. So we don't want to confuse that. So collision is not stopping convergence, And at the time, the guys here made a clear correlation between plate convergence and crustal deformation, saying that the consequence of India punching into Eurasia is extrusion of blocks. And it was reproduced here with a metal indenter being pushed into silly-putty with shear zones here localizing the extrusion of blocks towards the east, towards the free boundary, which is now the Pacific. I was a student, when I was a student exposed to that, I was saying, oh, I want to do geodynamics. It's fantastic, with the silly-putty and can reproduce the tectonic of Eurasia. That's fantastic. But then I had a closer look. What is here? These are bolts, nuts and bolts. And there's a plexiglass on top of that silly-putty. Why did these guys put some plexiglass on top of the silly-putty? Do you think they did that from the first attempt? Probably not. What happened to the silly-putty before they put the plexiglass? Went up. Couldn't go down because it's on top of a plate, of a table. So it went up. But it was not what they wanted to show. So I said, okay, what if we want to show extrusion? Well, let's put a plexiglass on top. Then the silly-putty has no choice than to go to on the side. So it was a bit disappointing for me as a grown-up now scientist when I realized that, because these guys were some of my mentors. But at some point you need to kill the father. At some point you need to, if you want to go beyond, you need to go to understand what was their bias and where you can go further. And don't take me wrong, this model was fantastic at the time. Even it was a bit biased, but they managed to show what they wanted to show, and it's been very influential. Maybe too much, because now most of tectonic plates or orogenic belts are explained by that process, which I think is not very compelling after all. But it's been very influential and stimulating. So what it also shows is that they considered here that the lithosphere is a single entity, and in zones of plate collisions, the lithosphere is probably thickening homogeneously, except that it's been dissected by lithospheric scale shear zones that allows for extrusion. And we come back to that. Oh, maybe I don't know if I'm not. No. So why this model? Because these guys worked also where there is an explanation. It was the onset of the use of satellite images. So they were looking at Asia and India from the top. Can you see up and down motions when you look from the top? No. So they couldn't account for that. But still, that's the place, the highest topography on Earth, And if you're not accounting for that in your model, you're missing something important, of course. But what they could see is offsets of rivers, offsets of sediments, offset of geological features from the top. So they were limited by their technology, which was fine. It was very important to develop that at the time, in the 70s and 80s. I was a student at the time. I saw that development, and it was great to go from outcrop scale investigations to Earth scale. That's really what was allowed by that revolution. But at some point, you need to move further, and you need to take into account thickening of the crust and topography in this area. So what they did, they proposed that the lithosphere is deformed homogeneously, but some other models were proposed, and that topography was, in that case, would be related to removal of the thick lithospheric root, dense lithospheric root, would pull down the topography, would be gravitationally removed, and boom, there will be a rebound, and that explains the topography in Tibet. That's how they got out of that dead end where they put themselves. But other researchers proposed that there was decoupling between crust and lithospheric mantle with subduction of the lithospheric mantle of the continental part, and they call that continental subduction. And this might lead to retreat and break off. These are the terms that were proposed, and delamination at the interface between the upper crust, the upper plate, and the lower plate. So that brings us to the present day paradigm. The lithosphere is subdivided into rigid plates that are moving relative to each other. And mountain belt formation in that frame is related to plate convergence, mostly, which brings magma from the mantle to the crust, and that leads to crustal growth of continents. And then there are different types of convergent plate boundaries that are involving either oceanic plates on both sides, and that's only growth of crust by magmatic processes. That's the case in the West Pacific for most of it. In the East Pacific, there is an oceanic plate converging towards continental plate, so it's adding some magma to the continental plate, but here mostly the mountains grow by deformation, shortening of the crust, thickening, that is then readjusted by isostatic rebound and leads to formation of mountains. And then there are collision plates with two continental plates that are converging towards each other. And we'll see that part of that lithosphere is subducting, part is forming the orogenic belt, and that's the alpine Himalayan belt. In that frame, mountain destruction is mostly invoked to be related to erosion and isostatic rebound, and the example here of the Alps, a young mountain belt, compared to a peneplain, here the Precambrian basement of Madagascar, but you can probably make the same picture of India with sort of a flat, rounded topography. And here the idea is that mountain building is resulting from shortening and the thickening of the crust, which with isostatic rebound makes a mountain that is followed by erosion, and the root is getting closer to the surface as material is removed from the top. And the Wilson cycle, in that Wilson being one of the guys that proposed that tectonic cycle, we can start anywhere, but we can start here with a continental rift that marks the onset of plate divergence. That leads then to opening of an oceanic basin, thinning of the lithospheric mantle. And then there is a switch from divergence to convergence that is accommodated by one plate being subducted beneath the other. And that's actually a question, where does it start? We don't have a good example of a starting subduction today. And it should start where there is a weakness in the lithospheric structure, but also where there is gravitational instability. So it might start either at oceanic ridges or along margins. And if we think in 3D, one good spot might be also the transform faults, because they are putting next to each other plates with different densities and weight. So that there might be also both a weakness in terms of mechanics and a gravitationally unstable situation. And then subduction leads to collision, mountain belt formation, and destruction by erosion. So we'll come back to that. That's a first order apprehension of the tectonic cycle, but there are some problems. So I move right away, right into these problems. So the next few slides, and then we take another break. So the first, and Malika has been working on that, is the generation of high pressure, even ultra high pressure rocks. These rocks are in a field, in a pressure temperature diagram that is much beyond the thickness, the depth of the maximum thickness crust. So that means if they are crustal rocks, that they were into the mantle. And now they have been sampled in Ladakh, in other places, in the crust, at the surface. So that means pressure is going this way. That means that they've been buried and exhumed. As if we take the model of tectonic accretion and mountain building before integration of these high pressure rocks, and even ultra high pressure, when we had blue schists, meaning pressure of the, let's say, equivalent of 40, 50 kilometers. With eclogites, it starts also to be on the edge of current day crustal thickness of 50 kilometers, 60 kilometers. But we can still explain it by just crustal processes, meaning that that's about 60 kilometers. That's the Alps. That's the cross-section of the Alps where you have the European plate going beneath the African plate and tectonic units being accreted here to form the Alpine wedge. And it's like a sort of a plane where the plate is going like this, but there is some kind of buttress that doesn't allow the crustal units to go down and contributes to make the orogenic belt. So if you have rocks that are here now at the surface that went to 60 kilometers, the idea was that there was burial and then exhumation thanks to erosion. But if you have rocks that went all the way to here, that means that they have to go beneath the plane and then go up again. So I have to say, I forgot I was not supposed to be here. I should go back. That was quite complex in that frame. So there was another type of models that accounted for that, which is this continental subduction, meaning that both the lithospheric mantle and the continental crust, here represented in brown, was entrained in subduction. And that was reproduced in, with also silicon and sand in a big tank of honey analog models. And this guy managed to, it's a Russian guy, Shemenda, managed to drag the continental crust with the lithospheric mantle, but then at some point he managed to decouple mechanically the brown from the green, and that's related to the presence of this weak layer in black, but also to the buoyancy of the brown. The brown is less dense, more buoyant than the green. So at some point, which is this stage, the brown decouples from the green, and its main driving force is buoyancy that overcomes the mechanical coupling and the strength of the coupling between these two units. And in this model, he also has full erosion. He had a sort of aspirator, how do you call that? Vacuum? No? Vacuum cleaner? What is the name? Suction, yeah. So he could erase as soon as this unit was coming up at the surface. He erased it, so it drove the system to have this point being exhumed all the way back to the surface. So it somehow explained how we can have these rocks buried down to depth and then exhumed back to the surface. It was also a very nice idea. So that's first thing we need to integrate in the Wilson cycle that was not in the first version. Second thing, extension of orogenic crust. Well, that was mostly identified in the Basin and Range region of Western North America. In this area of desert, that's in the Whipple Mountains, in the Basin and Range. And you see these more red units are actually volcanic and sedimentary units with the bedding like this, and they are in contact with gneisses and granites. And the contact is like this. Very shallow dipping, horizontal, with kinematic criteria that indicate a strong simple shear component in between the two units. And as the bedding is like that, that means that the bedding was horizontal to start with, so it's been tilted to its current day position. So these were called detachments and led to the definition of metamorphic core complexes. So at first, it was addressed by a kinematic approach with the pure shear, simple shear models of Mackenzie and Wernicke. Here, a pure shear model explains symmetric distribution of normal faults and in the ductile crust and the thinning, more horizontal, marked by horizontal layering and structures in the ductile crust. Whereas simple shear, there was a shear zone affecting the full mantle the full lithosphere, crust and mantle. But this was nice to distinguish between brittle and ductile deformation, but this was not really efficient at describing the full structure. Indeed, there is no such thing as a thinning of the crust localized in the Bayesian range. The Moho is flat. So it doesn't have this structure. The Moho is flat, is like this. And a more compelling model for that, to explain the diversity of structures, is the one of Buck, 91, where he relates the style of extension, metamorphic core complex, wide rift, and even narrow rift, with the thermal state, which controls the rheologic, the mechanical state of the crust. So when the crust is hot, it has a thick ductile part and a thin brittle part, and this will lead to only limited faulting, only to the top part, and faulting will be associated here with flow of the ductile part into the space created by the normal faults. So that will result in tilting of the first normal fault, which was here. So it's been tilted, and that's been tilted is no longer active. It's no longer in the right position to be active. So another fault will be activated, which is going to be tilted as well, and so on. So the last fault is here, the one that is active, is at the right position to be active, and all the other ones have been tilted, and that creates a horizontal detachment. Very nice way to produce a horizontal detachment. The wide rift, which is the current day situation for the Bayesian range, with all these riddles, are Horst and Grabens, is explained by a less hot crust, so a bit more strong, with a thicker brittle crust, but some ductile crust, that redistributes deformation from one place to the other by flow, horizontal flow of that weak ductile crust beneath high-angle faults. And this has been actually verified by a GPS monitoring of all the motion here on the Western North America, where they had put a network of GPS, and they could show that one fault was active here, and a few years later this one, and then this one, and then this one. So all these faults are active at once, at the same time, on the scale of a few years. You know? That means all that this area is undergoing extension, you know, but it's distributed over 1,000 kilometers. And then the narrow rift, that's when the crust is cold, very resistant. Normal faults are going all across the crust, and basically the distance between the normal faults allows you to identify the thickness of the crust. And that's what is happening in the East African rift, for example. So why, in this zone where the Pacific plate converges towards the North American plate, is there extension? That was also a big question. You know? Nobody would expect that in this region. And by looking at the structure, the two-day structure of the Bayesian range, people realized that first the Moho is flat, and it's flat at 25 kilometers. And when geologists measured the amount of stretching associated with each of these normal faults, Horst and Grabens, they realized that it's been stretched by a factor of 2. So it was 50 kilometers to start with. So it was a thick crust. And the force then they evoked to explain that is the gravity force. So in zones of thick crust compared to zones of normal thickness crust of 30 kilometers, there is storing of gravitational potential energy, which is related to the difference in the weight between the highland and the lowland. The rho density, G, Z. That's the weight. So that's the difference of weight between here and there. And you can see it here, and that's the weight in the highland. So we go from a density of 2.7 of the crust to a density of 3.3 in the mantle. So here we have crust all the way around, up to this, down to this isostatic compensation level. Whereas here in the lowland, you go from crust and then change density from 2.7 to 3.3, boom, increase the weight. And these reached each other at the isostatic compensation level. and the purple, the pink area corresponds to gravitational potential energy stored in a zone of thick crust. And it was proposed that the formation here was related to a change between mountain formation related to plate conversions to destruction related to gravity. Gravity overcomes plate tectonics. We'll come back to that later on. But that was the first time it was invoked as a tectonic force, gravity force. And the last thing is exhumation of high temperature molten orogenic roots. So in many orogenic belts, and you know that from India, well, you find high pressure rocks, but you also find high temperature rocks. So that means that there has been a change in geothermal gradient from low to high. And myself, I worked a bit, that's where I come into play. Worked a bit on that because I started, as I told you before, in this Velay region, in the French Massif Central, that's in the central part of France. And all the pink are migmatites and granite. It's half of the map. So you cannot avoid it. And it's the same in India, right? More than half of the maps are migmatites and granites or granulites. So what I realized at the time, this was the cross-section proposed by a guy from Montpellier, Matt. And you see here, basement, cover, basement in pink, cover in white, thrusts, duplicating the basement and the cover, and the domes. So this is a dome. Domes here expressed as antiforms, related to crustal duplexes, crustal thrusting on top of each other. Where are the migmatites? Well, migmatites are supposed to be here. Granites synchronous to deformation, plutons. Where do they come from? They are rooted in something that is rigid. There is something that is problematic here. And most of all, I think I'll come back to that later on, this problem, but another thing I want to show here is, in order to have these rocks, which were metamorphic at the time of orogenic evolution, which was corresponded to about 15 kilometers depth, that thickness. In order to put them back to the surface, you need to remove this rectangle. And the only sediments that are identified of that age are here and there, these small gray things, the upper Carboniferous basins. And you need to put, these are the gray triangles. So in order to exhume these rocks by erosion, you need to put the pink rectangle into these gray triangles. You see that obviously it's not going to work, right? You can push hard, but it's not going to fit into these small triangles. And especially the sediments are less dense than the metamorphic rocks. So it's not even pushing is not going to be a solution. So how do these rocks being exhumed? And I come into play. That's me in 1990 something. Sorry, I'm getting old. I discovered the apple at the time, so I was happy. And I changed this cross-section during my master study. First I realized that we worked on that project, so it's a zoom of this structure, the Velay dome. And it's really a dome. It's delineated by structures, by lithologic units that are surrounding this zone. And it was part of a mapping project which involved about 10 academic centers in France with different people working on different rocks. People from Clermont-Ferrand. Clermont-Ferrand is a central part of the Massif Central. They are specialists of granite and plutonic rocks. And they were mapping granite. As long as they could see granite in the rock, they say granite, 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 granite. People from Montpellier, southern France, specialists of metamorphic rocks. They looked at schists. And as long as they could see schists in the rocks, they map it as schist. And this is 20 kilometers. And the first field trip we had together, the discrepancy between these two contacts, granite and schist, people from Clermont-Ferrand put the contact between granite and schist here. people from Montpellier put the granite and schist contact here, 20 kilometers difference. Okay, wow. I was a student at the time, or a master student. These guys don't know what they're talking about. They don't agree on the name of the rock. Well, in between, the rocks are migmatites, a mixture between granite and schist. And it was a difficult problem. You know? And these migmatites, they look like this. So you have a part that is gneissic, a part that is granitic. Some would look at this part, some others would look at this part. And no one would consider the mixture. They have a foliation, which is okay for structural geologists. It's difficult because it's not as well organized, but still there is some kind of preferred orientation, so a foliation, which we'll see tomorrow is recording orientation of solid parts in the magma, in the melt, at the time of coexistence of the two. So it records deformation in a partially molten state. The guys from the schist said, okay, no, that's inherited structures from the protolith. So we pretend the granite is not there. We just measure the structures in the schist or the gneiss, and we pretend the granite is not there. The guys from the granite said, okay, granites have no preferred orientation, so that's not an orientation. No, granites, magmas are isotropic. Well, okay. And this foliation, when you measure it, it's concentric. And the difference in distance between this point and this point is 100 kilometers. It's from here to there. 100 kilometers. So I tried to do the first cross-section of this area, and I realized, wow, this dome is 3 times the crustal thickness. This has to be a crustal scale process. It's not something that is just a granite coming from nowhere. And Matt is describing like this. Granites are kind of disturbing the picture, so we try to avoid them, not to see the real rocks, the ones that are important, the metamorphic rocks. So, well, if you make that, you miss half of the story. So I transformed that section like this and considered that all these migmatites are crustal scale, and here I think you feel the ductility, the flow of these partially molten rocks that will rise up and form domes, in different parts. So we'll deal with that tomorrow morning. That's for Malika. Who was next to me? Michel. We've been, that's a friend of mine. We've been close friends since the first year of study. And he was visiting here in 2018. Malika has come also to visit in Toulouse. So that's the other lesson. When you choose friends, be careful. Huh? It's going to last longer. If you meet people in your studies, make sure you choose the right ones. Okay, so that's the second conclusion, the conclusion of the second part. So if you want to understand the evolution of mountain belts, we need to integrate results such as ultra high pressure rocks, migmatites, extension of orogenic crust, that will allow us to address the question of transition from low to high geotherm, the transition from crustal thickening to crustal thinning, and then the process of exhumation of metamorphic rocks. And you want to really be careful to distinguish plate kinematics, the motion of rigid plates, convergence, divergence, from deformation. Deformation is shortening, lengthening, so that's the scale of rocks. And then crustal deformation, and that's the terms that are the most confusing, is extension. I think tectonics people mean crustal thinning. Compression, where they think of crustal thickening. But the same terms, compression is used for plate, so for mechanics. I don't know if you have rock mechanics, but rock mechanics is trying to make the link between strain and stress. And stress is called compression. We use one term to describe 2 things. Lots of confusion in the literature. So if you think you don't understand these papers, it's not your fault. It's because there is confusion between physics people, rock mechanics, and tectonics. Extension and compression are terms to be very careful with. So distinguish deformation from dynamics and from plate kinematics. And then we'll look at the force balance and at the thermal balance, the thermal evolution, but we'll develop that later on. And we'll integrate from lithosphere to grain scale, and we'll look at the mechanical behavior. We integrate metamorphism and magmatism and deformation, and we also, as an observable, look at the evolution of topography, which is going to be the next hour. So another short break, still have some energy.